Every millisecond, search engine bots ingest millions of web pages. They are mechanical parsers indexing the web at industrial scale. Algorithms prioritize computational logic over linguistic nuance. They parse the underlying codebase to evaluate structural integrity and resource delivery. Search engines evaluate technical signals embedded directly into a site's architecture. A site remains invisible to the index if its foundation fails to meet specific algorithmic requirements. Ranking a modern web application requires three sequential phases: server crawlability, browser rendering stability, and semantic machine parsing. The process begins with the server's response to a bot's request. The second phase involves the browser mathematically measuring layout physics and loading speed for the user. Managing SEO as a verifiable stack of these interconnected technologies is the only way to guarantee a site is discovered and indexed. Every web interaction starts with a search bot arriving at a server to request the site's HTML code. Modern web development has two paths: client-side and server-side rendering. With SSR, the server pre-builds a complete HTML document, delivering fully populated data immediately. Client-side rendering delivers an empty shell and heavy JavaScript. The bot must execute the code itself. This execution phase impacts the crawl budget, which is the finite amount of computational power Googlebot assigns to a single domain. Forcing a bot to execute JavaScript in a deferred rendering queue rapidly depletes this resource. Depleted budgets lead to server timeouts, partial indexing, and content that never reaches the search index. These rendering inefficiencies scale poorly on large enterprise and e-commerce platforms. E-commerce filters or faceted navigation create thousands of URLs with heavy parameters and duplicate data. Complex environments require server-side rendering to ensure the bot parses the correct product data without wasting compute time. Effective traffic control also relies on strict robots.txt directives and canonicalization strategies. These directives tell the bot to ignore duplicate filter pages, focusing the crawl budget on unique, high-value product pages instead. Ranking depends on a server environment that delivers fully rendered content instantly, preventing the bot from abandoning the crawl. After the server delivers the payload, the evaluation moves to the browser, where the human experience is measured. Google uses Core Web Vitals to provide a strict algorithmic quantification of page performance. Largest contentful paint is a product of server response times and the specific load order of visual resources. Interaction to next paint measures the time the main thread is blocked by background tasks. The most visible metric, and the one most likely to trigger a penalty, is cumulative layout shift, or CLS. CLS measures visual stability. If an unoptimized image loads late and displaces the text, it shifts the layout and disrupts the user. This recalculation of node positions damages the site's stability score within the search algorithm. Layout shifts are usually caused by dynamically injected ads or images that lack defined size attributes. The engineering solution involves using CSS aspect ratio boxes to reserve space on the screen before any heavy assets are fetched. Reserving this geometry prevents the browser from recalculating text positions when the image finally arrives. The layout remains stable. This requires hard-coding width and height attributes in the HTML or implementing CSS aspect ratio configurations. These dimensions must be set before the assets are even requested from the server. Passing Core Web Vitals is simply a matter of engineering absolute deterministic stability into the browser's rendering process. Once the layout is stable for humans, the focus shifts to defining the meaning of that layout for machines. Semantic HTML provides a logical document structure, but it lacks the detail required for deep search parsing. HTML describes how to display information, whereas search algorithms require a definition of the underlying entities. This definition is provided by JSON-LD, a script that uses the Schema.org vocabulary as a translation layer. This code transforms passive text into rich snippets, making the data actionable for the search engine. Implementation begins by explicitly defining the core entity type of the URL, such as a product or an article. The data must then be formatted into a JSON object that adheres strictly to Schema.org requirements. Missing mandatory key-value pairs, like price offers or product names, will cause the entity validation to fail. The script is injected into the document, where the data must perfectly mirror the user-facing text to avoid penalties. Structured data is the final bridge that turns a web page into an indexed node within Google's knowledge graph. Unifying these components creates a cohesive architectural pipeline for discoverability. First, the server delivers a fully rendered payload, which preserves the bot's crawl budget. Second, the DOM locks into place immediately, achieving perfect visual stability and a passing performance score. Third, the JSON-LD script feeds a clearly defined entity directly into the search algorithm. Search engine optimization succeeds only when these three technical events align perfectly. High-quality content remains invisible if it is blocked by inefficient JavaScript rendering or unstable browser physics. Commanding modern search rankings requires precise server-side execution, deterministic layout physics, and the explicit structuring of underlying data.